Here's a presentation on the 555 timer lab. First part, we're going to design a one-shot or a monostable timer, and the formula is time high equals 1.1 times R times C. I rearranged this using a little algebra, and I have R, and we're going to use the 47 microfarad because that's what's listed in the lab, and it's a large one that will be able to get the 5-second pulse. So put it in the formula and I come up with 100K. So here's our monostable circuit in multisim, and it is 5 seconds or pretty close to it. It's hard to measure with an oscilloscope with the multisim and set this one up, but essentially we have the 100K over 47. Here's our decoupling capacitor. And over here we have a 10K pull-up and a switch. This switch is to provide a momentary signal to our trigger, and once it's triggered and released, it starts the count. And it'll time out to the 5 seconds. So the result was pretty close to 5 seconds. Here's the mathematics behind the first Astable timer that we asked for, 6.2 kilohertz and a duty cycle of 60%. So the first thing we need to figure out is the period based on our frequency of 6.2 kilohertz. We come up with 161.3 microseconds. Our time high is going to be our duty cycle times our period, which comes out to 96.8 seconds. For time low, we're going to take the period and multiply it or subtract it from the time high, and we're going to end up with 64.5 seconds. And we're going to put it in the formula. We have RA and RB, time high over 693, which is a constant based on that exponential charge discharge rate, times our capacitor. And I'm just going to choose 0.01 microfarad because it's on the lab and sounds like a good size. And that we come up with our formula of 13.9 K ohms. And then RB, we use the formula and we come up with 9.1. And we have to sneak up on it a little bit to find RA. So we're going to subtract RB from the combination, and we're going to come up with 4.5 K. I chose 9.1 K and 4.7 K because those are available resistors and they're in our kits. Here's our Astable circuit trying to receive this 6.2 at 60%. So here's our 4.7K and our 9.1K and our 0.01 microfarad capacitor. And I've hooked up a frequency counter and an oscilloscope. And here's our decoupling capacitor. Here's our output from our 555 time reference circuit, and we nailed it. 6.2%, 6.2 kilohertz, show our frequency counter, and 60% duty cycle. So when I use cursors on our output waveform, I calculate out 59.4%. I'd say that's a pretty good hit. Here I use the same formula for calculating our second circuit. This time we want 6.2 kilohertz, but we want to change the duty cycle to 70%. So I go through the calculations. I come up with 6.8K and 9.1K, and I'm sticking with the same size capacitor. Here's our circuit again, this one with our different resistor size, 9.1, 6.8K, and 0.01 microfarads. Again, I'm using the oscilloscope and our frequency counter. Here's our results from our second circuit, and 6.3 is very close to the 6.2 kilohertz. And again, using cursors and doing the calculation, I come up with 69.6%. Very, very close to 70%. I would say that we nailed it.